Hello, this is Mark Anderson for Kellogg Community College, and we're going to be looking today at Chapter 1, Section 3 of Trigonometry. This is a little bit of an overview about functions, some of the things about functions, their correspondence, and some other things you can do with them in terms of domain and range, finding intercepts, and graphing. So it's just a scatter shot of all the different things that we have done in 121. So this is going to pinball around with a lot of different information. The first thing I want to do is cover just some basic vocabulary. Relation is a correspondence between two data sets. So domain are the x values, and the range are your y values. The domain is the independent, or the x is the independent variable, and the range is the dependent variable. X corresponds to y, y depends on x, and we're going to see that here in a little bit of these problems, these mappings of these problems. And one of the important things about functions is that for every x, there is one y. So if x branches to more than one y variable or y location, it is not a function. And we'll see that with some graphing, but if you take a look at this here, if I say that for every x, or if this is the domain, and this is the range, so for every x there is one y value, or one specific y value, then this part A, one part A, is not a function. This here, again with our domain and range here, you can see that every single x has one specific y value, therefore this is a function, so yes. If there was a situation, like let's say there was some postgraduate, like post-college graduate, like, let's say, maybe PhD, and let's say PhD also went to the same average income, this would still be a function because there's still one arrow coming from PhD. You wouldn't have PhD branching to 2 to 3 different average incomes since this was tabulated using the average formula. But again, I just made this up. In reality, the level of education would actually increase the average income here. But I just wanted to show you that you can have multiple arrows going to the same range, but you cannot have the domain going to multiple ranges. Taking a look here, we're going to make a map out of this with our domain and range. And our domain and range is going to be literally our x and y. So our x's are -2, -1, 3, and 4. And our range is going to be the 2 goes to 5. This goes to 3. And I'm putting these right next to each other just because it's easy to do it that way rather than putting them in numerical order top to bottom. And then 4 goes to 12. This right here is a function, so yes, it's a function, and therefore the domain is going to be the set. And it's the finite set, so that's going to be -2, -1, 3, and 4. Notice finite sets are just written inside of these brackets here. And the range is going to be the numbers. Now I will order this from lowest to highest: 3, 5, 7, and 12. I'm going to move this down a little bit, so if you need to pause it, go ahead. I'm going to move this to our next two examples, make maps of, like these parts were maps, we're going to make maps of these as well. So let's go take a look here. It looks like I'm going to have 0, 1, 2, 3. This is my domain. And then my range is going to be literally my y values here. So 0 gets mapped to -2. 1 gets mapped to 3. 2 gets mapped to 3, which is okay, and 3 gets mapped to 7. So right here, I definitely have my domain and range all set. This is a function. So my domain is the finite set of 0, 1, 2, 3. And my range is the finite set of -2, 3, and 7. This is a finite set. Notice there are only 3 elements here. We wouldn't list 3 twice. So that is a function right there because it's definitely one-to-one. Now, looking at this here, we've got our domain and range. And something funny is going to happen here. I got my -4 going to 4, -3 going to 3, -2 going to 2, -1 going to 1, and I have -4 also going to 0. So here I have a situation where I have one element of my domain is going to 2 elements in my range. Therefore, this is not a function because this would violate my rules about functions. Now, we're going to take a look at some basic graphs here, these 3 in particular, and ask if it defines y as a function of x. And we have a test for that. When we do graphs, we have something called the VLT, or the vertical line test. And the vertical line test states that if a vertical line goes through more than one location on that graph, then it violates the vertical line test and it is not a function. The graph of y is equal to x cubed looks like this. It has a intersects at the origin and continues going on from here, and it passes the vertical line test since every single vertical line only intersects with the graph at one location. The absolute value of x is also has intersects at the origin, and it looks like this, and that also passes the vertical line test. So yes, it's a function of x. Yes, it's a function of x. Yes. Well, wait a second here. In this graph, this is going to be a square root, but without actually getting into the specific graph here, if I just look at the positive square root of 1 minus 2x, without getting into too particular here, it's going to look like this. It will be shifted based on this inside of the problem here, the 1 minus 2x, if you plotted all your points. But then if I put the minus part of it on, it will look like this. So this violates the vertical line test, and since it violates the vertical line test, then no, it is not a function of x. Let's go and take a look at some more pieces of this here. In this problem, we have x squared plus y squared, and let me get my pen ready here. If I solve for y, I would move the x to the other side by subtracting it. Because let's say I wanted to try to type this into a graphing calculator. So now I have 1 minus x. Take the square root of both sides. Y is equal to plus or minus the square root of 1 minus x. And for the same reasons as on the previous side of this worksheet, you'd have another graph that would look like this. And so it would violate the vertical line theorem. This function actually, this is actually a function. I won't show you a graphical representation of it, but it does have a missing piece. It actually has a hole. This graph does not exist at -2, because at -2 on the graph there is an asymptote line. And we've seen some of these in Math 121, because what happens is that the equation will get as you get closer to that -2 value, it's going to be undefined. So what you're going to have is you're going to have this line, and this is one possibility if we graphed it here. I didn't actually graph it beforehand, so you feel free to type this into a graphing calculator and see what this looks like. But you can see that it is a function because it doesn't violate the vertical line test, because at that excluded value, where -2 gives you an undefined answer because it's division of 0. This is a situation where, hey, you're still going to have a function even though it's not continuous. And one of the changes I made to this problem on my worksheet here, is that this is going to be plus y squared. So this is the definition of a circle, and a circle definitely violates the vertical line theorem infinite number of times. So 8 and 10, not functions, but number 9 is a function based on its equation. Alright, so for problem number 11, there's actually 8 parts to it, and that 8 parts really gives you kind of an algebraic workout. Let me kind of move that here so we can see it. Not only does this give you a good algebraic workout, it gives you actually some good notational workout, which means like, well, first of all, this equation right here is a y equals equation, and this is the function of x. So if we plug 0 in for x, or what is my value of the function when x is 0? So what I'm going to do is plug 0 in for x, so part A, get my pen turned on here. Part A is going to be plugging my 0 in for x, which is going to be negative 2 times 0 squared plus 0 minus 1. Well, 0 plus 0 minus 1, my f of 0 is going to be negative 1. Part B is the same thing as part A, except I'm plugging 1 in for my x, so my f of 1 is equal to negative 2 times 1 squared plus 1 minus 1. So this is going to give me, do some more simplification, my f of 1 is going to be negative 2 times 1, which is negative 2 plus 1 minus 1. So that's going to be equal to negative 2. So my f of 1 is equal to negative 2. Letter C, I'm going to plug negative 1 in for my x, and this is going to be a little bit trickier because you have a exponent there. Be very careful if you're going to do all of this on your calculator without writing out any work. You be very diligent about these parentheses because this is negative 2 times positive 1. This negative 1 inside this parenthesis is going to be minus 1 minus 1. Following order of operations correctly here, we're going to have negative 2 minus 1 for a total of negative 4. Part D is plugging negative x into this equation and then doing some simplifications. So my function of negative x is going to be to plug a negative x in for every instance of x. So this is negative x quantity squared plus negative x minus 1. So this is going to be negative 2 times x squared, because negative x squared, or negative x times negative x is positive x squared. This is going to be minus x minus 1. And that is my f of negative x simplified, because you cannot collect like terms, they're different degrees. So there's my letter D, negative 2x squared minus x minus 1. Here's letter E. Now it's interesting because the negative is on the outside, so that's taking my my negative f function of x is going to be taking a negative to the entire equation. This negative 2x squared plus x minus 1, which makes everything opposite of its original positive or negative nature. So this is going to be positive 2x squared. This is going to be minus x, and this is going to be plus 1. Obviously, this is the distribution of the negative 1. When we get to letter F, you'll notice this is an x plus 1. I'd kind of like to start over on a blank screen, even though you will have plenty of room there. I just am going to quick erase and bring this back here. So what I'm going to do is plug in for f my function of x plus 1. I am going to plug that x plus 1 in for every instance of x. Now what I will do is use my FOIL to basically FOIL this out. Now on the side work here, I'm going to take my x plus 1 and square it. Please understand that squaring a binomial is not just distributing the 2 to the inside like x squared plus 1. It's actual FOIL. So this is going to be x squared plus x plus 1, which is x squared plus 2x plus 1. Therefore, this is going to be negative 2 times x squared plus 2x plus 1 in parentheses plus x plus 1 minus 1. Drop the parentheses since there's nothing else to do here. I'm going to distribute the negative 2, so this is negative 2x squared minus 4x minus 2 plus x, and then plus 1 minus 1. Now we get to collect like terms. There's no other x squared in the problem, so negative 2x squared is your leading term. Then you have negative 4x plus x, this is negative 3x, and then, because it's negative 4 plus 1, and then 2 plus 1 minus 1 is just the minus 2. So that is our answer for letter F, which is our f of x plus 1. Now what we'll do is we'll plug in our 2x, which is a little bit easier. So that was letter F. Let's go with letter G. So letter G is plugging in for every value of x, 2x. So this is going to be negative 2 times the quantity of 2x, quantity squared, plus parenthesis 2x instead of x minus 1. So we'll do some work here. This is going to be negative 2 times 4x squared. That's just 2x times 2x is 4x. And then, since that's a monomial, that's an easy fix there. 2x minus 1. So this is going to be negative 8x plus 2x minus 1. On to letter H, another binomial, and I will have enough room to do this here. This is my f of x plus h. So in every instance of x, I'm going to type in my x plus h. So there's my x plus h quantity squared plus x plus h not squared, and then minus 1. Alright, so off to the side here, I'm going to have my x plus h. So this is my FOIL of x plus h quantity squared. X times x is x squared. This is going to be hx. This is going to be hx, which is going to be 2hx when I'm done with this here. And then what I will have is I will have h and h, which makes h squared. So this gives me inside here x squared plus 2xh plus h squared, which means that my negative 2 on the outside of this binomial is going to get multiplied by this trinomial, x squared plus 2xh plus h squared plus x plus h, since there's nothing to do inside that parenthesis, minus 1. Distribute the negative 2, so negative 2x squared. Distribute the negative 2, so this is 2xh times negative 2, so negative 4xh. And this is negative 2 times h, this is negative 2h squared plus h, or plus x plus h minus 1. There's no other simplification I can do because none of these terms can combine. And that's my answer for that problem, f of x plus h. So a little crash course on FOIL, and it's also a little bit of algebraic manipulation, a little bit of weightlifting there to get you ready for the accuracy we're going to need. Now, to wrap up the third part, the third page of this first part of the video, is we're going to look at domains of functions. And when we look at the domain, we're going to have two things to consider. You will always have restrictions on your domain if you have a denominator, because your denominator will have some situations where if it's ever 0, you're going to have division of 0 error. So denominator gives you your divide by 0 error. Divide by 0. And that's where you should look out for that. And also, if you have a square root, square roots can never be negative. So square roots have to be greater than or equal to 0, because you cannot have the square root of a negative number, because the square root of a negative number is imaginary, and you cannot divide by 0 because that's undefined. So let's go and take a look at these problems and see, first off, in problem number 12, does it have a denominator? Well, no, it doesn't. Does it have a square root? No, it doesn't. Since it doesn't have a denominator nor a square root, then your domain is going to be the set of all real numbers, which is kind of nice because there are no restrictions. But if we look at problem number 13, does it have a denominator? Well, yes, it does. And since it has a denominator, we have to look to see when we could plug a number in for that problem and get a division of 0 error. We ignore the numerator because the numerator will be some 0 or non-zero. It doesn't matter. It's going to not give us the division of 0 error. So let's look at problem 13 here. What I should do is set the denominator not equal to 0. See, we don't want that denominator to be equal to 0. Therefore, we have to now set this problem up so we solve for the values that would make it that 0. Some of you might have thought in your head that the answer is 2, but that's not quite the full answer here. We're going to add 4 to both sides. So x squared is equal to, or not equal to, we don't want x squared to be equal to 4. If we take the square root of both sides here and here, we get x cannot be equal to positive or negative 2. and that's true. 2 times, 2 times 2 is 4. 4 minus 4 is going to be 0. And negative 2 times negative 2 is 4 minus 4, which is 0. So my domain is going to be just this example here. We're going to say that our domain is going to be the set values of x where x cannot be equal to negative 2 or x cannot be equal to positive 2. This is going to be, x can be any other real number except it cannot be negative 2 or positive 2. Because who cares what the numerator is going to be? The division of 0 is what we're trying to avoid. For problem number 14, we're going to do the same thing. We notice we have a denominator, so I'm going to set that denominator to not equal 0, because we do not want that denominator to ever be 0. To solve this problem, you're going to do a little factoring. You're going to factor out an x, which gives me x squared minus 4 cannot be equal to 0. And we've also, if you notice that x squared minus 4 was part of the original problem, which is why I did it here. Therefore, we're going to have two problems where we're going to have x is not equal to 0, because if we plug 0 in here, we'll get division of 0 error. And from the previous problem, we have our x squared minus 4 cannot be equal to 0, which we solved over here. So x cannot be equal to negative 2, x cannot be equal to positive 2. And so if we kind of put all these inside of our set notation brackets, we've done our domain. The domain can be anything on x as long as x is not 0, not negative 2, or not 2. These would all be vertical asymptote lines where the graph would diverge at these points there, or at these places. There would be no, the line would not exist at these three locations because of division of 0 error. Now, when we start with problem number 15, is we start with square roots. And square roots cannot be negative. You cannot have a square root of a negative number. So anything underneath the radical, we need to have greater than or equal to 0. And then we solve for x. Subtract 1 from both sides. Negative x is greater than or equal to negative 1. Divide both sides by negative 1 to get the x by itself. X is less than or equal to positive 1, because that flips the symbol. When we multiply or divide by a negative, we flip the symbol of an inequality. And this gives us our answer of x is less than or equal to 1, so our domain is going to be anything x as long as x is less than or equal to 1. And we can see that because as long as we plug in a number that's less than or equal to 1, this is going to be a positive number inside the radical. Same thing goes here for number 16. Since we have a radical, we're going to have to make sure that that radical is greater than or equal to 0. So we're going to have our negative x minus 2 is greater than or equal to 0. We're going to then solve for x, so we're going to add 2 to both sides. So negative x is greater than or equal to 2. And then we are going to divide both sides by negative 1. Which in turn flips the symbol, so x is less than or equal to negative 2. So as long as x is less than or equal to negative 2, then this problem is going to be positive inside here. So if you plug in, for example, negative 10 in for x, that will give you 10 minus 2, which is 8. The square root of 8 does not violate any domain issues. X is less than or equal to negative 2. Now things get a little weird when you have a square root in the denominator. Now we said our denominators cannot be 0, and our square roots have to be greater than or equal to 0. So if you look at those two sets, we need to make sure that our denominator is greater than 0. Because we can't have our denominator being 0, we also can't have our denominator being less than 0, so that means that our denominator has to be greater than 0, which is pretty easy because x is greater than 4 if you add 4 to both sides. So this is my domain of x, where x is greater than 4. Which is a short and sweet problem, but the difficulty is realizing that your denominator has to be greater than 0, not just greater than or equal to 0, because it's a square root in the denominator. Problem number 18 is kind of a neat little problem, and if you want to type this into a calculator, you'll see the answer right away. But let's just go through the process. I have a denominator, and since I have a denominator, I have to make sure that my denominator is not equal to 0. Now check this out. When I solve for x, I subtract 1 from both sides, so x squared is equal to -1, and then I take my square root. This gives me an imaginary number. And since x doesn't have any answers, then I actually have no exclusions on the domain. Because no matter what I plug in for my x, if I plug in a negative or a positive number, my denominator will never be 0. And since my denominator will never be 0, I have no exclusions, my domain is real. And if you take a look at your graph of this function, you will see that there is no excluded values for this problem at all. The answer is real. Since there is no value of x, I could put in no real value of x I could plug in to give me 0 in the denominator, or a -1 plus 1 to make 0. Haha. So problem number 19. To end this video here, I'll work with this because this has a square root and a denominator. So I have to do two separate cases. I have to take the case in the numerator of x plus 3, and I want that to be greater than or equal to 0. So I'm going to say my x plus 3 is greater than or equal to 0. So x has to be greater than or equal to -3. So if I plug in a value for any value bigger than -3, I will get a radical that's positive, or 0. Now, notice that in my denominator I have an x minus 2, so I have to set that not equal to 0. And I move the 2 to the other side, so x cannot be equal to 2. Well, this means that I have a set where x is greater than or equal to -3, but x better not be 2. So there's going to be a hole in the graph at that place, because there is not going to be any value that can be there, because if x is exactly 2, even though my numerator would be the square root of 5, my denominator would be division of 0. So these are the excluded values of x. X has to be bigger than or equal to, greater than or equal to -3, but it just can't be 2. Alright, thank you for watching the first video here for the first 3 pages. We'll have the next video for the next 3 of this session. Thanks for watching.